Hello everyone. In this video, we will learn how to integrate partial fractions. Well, there won't be any new technique. We just need to follow specific steps to complete the integration of partial fractions. Let me start with recalling what is a partial fraction. Yes, so we had two cases. A partial fraction is a rational function. Fraction is a rational function of one of the following forms. It's either a number over a linear term to the power j. I'll call them powers of linear, and or there is a linear term in the numerator over ax squared plus bx plus c to the power j. That I will call quadratic. And here I'm assuming for both of these guys, a is non-zero, and also for the second one, b squared minus 4ac is negative number. Well, for the other cases, this what we are doing will work, but will be a little bit different. Here in this video, I'm specifically working with this condition. Okay. Let us then start. Yes. So how to integrate case 1. I'll call this one case 1. Case 2. Okay, so for case 1, everything is easy. There is only one thing you need to do and apply the substitution. U equals to ax plus b. Note that a and b are constant, so du is going to be just a constant times dx. Generating that is easy, and everything will go easily to the end, okay? And you can turn to u integral, and u integral is an easy integral. Let's see this in an example, or two examples. Here, I have 1 over a linear case, so I have u equal to ax plus b, in this case 2x minus 1. That means that du is 2 dx. Since that's just constant, I can bring it to the other side so that when I'm transferring to u integral, that's easy thing to do. So here, then I will have equals to integral of half of du, that's for dx, over just u. So that's half of integral of du over u, and we know that that antiderivative of 1 over u is ln of absolute value u, and then plus c. We'll plug it in back, so ln of 2x minus 1 plus c. Well, indeed, this is so straightforward that I would suggest that you put or add this integral into the table, your integral table, integration table, so that whenever it comes up, you just use the formula and don't need to go over what we did right now, like a minute ago. Okay, so integral of 1 over ax plus b dx is 1 over a ln of ax plus b plus c. Okay, how about the other case? Okay, in this case, again, I have a linear case to the power 5. So substitution 3x plus 4 is u. Du is going to be 3 dx. Since 3 is just number, I will divide it to the other side or take it to the other side, so that changing to u integral will be easier. So here I have 5. Dx is a 1 over 3 du over, that's u to the power 5. Yes, So 5 over 3 integral u to the power negative 5 du. This is just power rule, and that will give me 5 over 3 1 over negative 5 plus 1 u to the power negative 5 plus 1, and then plus c. And well, I can plug it in back, so I will get 5. The denominator is negative 4 times 3 is negative 12. U to the power negative 4, u is 3x plus 4 to the power negative 4 plus c. I can take that one to the denominator, so 12 3x plus 4 to the power 4, and then plus c. And that's what we were looking for. Yes, integrated that. And all the partial fractions with the case 1 will give us that kind of easy integral. Okay, but how about the case 2? That's the key point. So how to integrate case 2. Okay. Well, for case 2, the number of steps is a little bit longer. So I will just quickly write down a few things here just to outline what we want to do. And then in some examples, I will explain what each step mean. Okay. Sometimes you don't need to follow all these steps, but few of them, and then get the answer. Okay, so the first thing is that what kind of functions we are dealing with. So remember that the case 2 is ax plus b over ax squared plus bx plus c to the power j. Yes, so if there is an x in the numerator, okay, the first thing you have to do is generate the derivative of this ax squared plus bx plus c in the numerator using that x. So use x in the numerator if there is any. If there isn't, just jump to the next step. Numerator to generate the derivative of ax squared plus bx plus c. And then when you generate that, you split into two pieces. When you have the part which has x and it has the derivative in the numerator, the other part has just constant numerator. So, and the split into two integrals. The first integral, which has the derivative in the numerator, it would just go ahead and use u equal to ax squared plus bx plus c. For the second integral, so second integral, that's now what you need to do. Complete square. Since we have assumed that b squared minus 4ac is negative, so that means that ax squared plus bx plus c, you will be able to write it as something like a times x plus alpha to the power 2 plus some beta to the power 2. So that's the squaring, completing squaring, and it will get to that point all the time. And then use substitution u equal to x plus alpha, that's constant. And when you do that, in the denominator you will get a term. So as a result, in the denominator, ax squared plus bx plus c will turn to au squared plus something squared. And that's where you need to use, I will write the last step, use trig substitution. So in this specific case, AU squared plus beta squared, you need to use U is equal to beta over root A tan theta. A number times theta, so that when you multiply here, you get tan squared plus 1 squared. Let's see this in example. So first, get rid of x, complete the square, and then use trig substitution. Let's see in some examples, and you will notice what I mean. Here, I'll start with the first thing. So the derivative of the denominator is 2x. I have to use the x in the numerator to generate 2x. So what do? Is I will take out that 3. I will multiply x by 2. That's the derivative. Since I multiplied the numerator by 2, I have to divide it by 2 as well. And that's x squared plus 9. That's the derivative of that in the numerator. And then the rest, you split that. So 1 over x squared plus 9 dx. Now we have two integrals. The first integral, the second integral. The first integral, now you see that the derivative of the denominator is in the numerator. So it means that if you set u to be equal to x squared plus 9, that will give you du is equal to 2x dx. And the integral will turn to integral of du over u, which gives me 3 over 2 ln of absolute value of u plus c. And then let me just write the final result here. This is 3 over 2 ln of x squared plus 9 plus c. So when you generate the derivative of that quadratic term in the numerator, everything can be done with this substitution, and it will turn into an easy integral, and you can integrate that. The second one, however, you have to do what we call square, completing square. But this term here is already complete square. So then the next step is use trig substitution. Remember that if we had x squared plus a squared, we use x equal to a tan theta. So here we will use the same idea, but a here is what? A is 3. So I'm letting x equal to 3 tan theta. And okay, so I will get -4 integral of 9 tan squared theta plus 9. Dx here is going to be 3 secant squared. So 3 secant squared theta d theta. Let me take out all the constants there. So the constants will give me -4 over 3 integral of secant squared theta tan squared theta plus 1 d theta. Remember that tan squared plus 1 is secant squared theta. So that means that the numerator and denominator cancel each other, and what we get -4 over 3 integral of theta, integral of 1 d theta. And that is just -4 over 3 theta plus c. But theta was it's already chosen here, yes. So theta x over 3 is tan theta, so theta is going to be tan inverse of x over 3. Maybe I should put this a little bit lower down there so that you notice later when you look at the notes that we did this. So that will give me -4 over 3 tan inverse of x over 3 plus c. Okay, so we found the first part, the second part. The first part gives me 3 over 2 ln of x squared plus 9. And the second one, negative 4 over 3 tan inverse x over 3, then plus c. That's the answer. Here, like the one that we had in the linear case, I want to also add this into your integral. So if you have 1 over x squared plus a squared dx, then this will be 1 over a tan inverse of x over a plus c. That's basically what we did on the left hand side, or the second integral was you can repeat it exactly all the time, and so since it's there, just use it. Okay, so you see, we first get rid of x, generating the derivative of the quadratic part and separating it, and then for the right hand side, here we didn't need to complete the square, but then we use the trig substitution. Okay, let me do one more example here. So this one is, again, we have x in the numerator, and this is down there. So I need to generate the derivative of the denominator, or the quadratic part. The derivative of quadratic is 2x plus 2. So I multiply x by 2, and so I have to divide the whole thing by 2. Then I do plus 2, and then I do another minus 2. So that's where I separate this minus 2. In the denominator, well, everything stays as is. Okay, dx here, and you will get 1 over x squared plus 2x plus 5 squared dx. Now, for the first integral, you see, we generated the derivative of the quadratic part in the numerator and separated everything else in another integral. Here, you just need to do u equal to the quadratic, and then du is whatever you have in the numerator. And while applying that substitution, you will get half of okay, let me just finish the whole thing. The whole integral, after doing substitution, returning everything back, it will be 1 over x squared plus 2x plus 5. There will be 2 here, there will be negative sign there, plus c. So there will be some steps there, but I'm just jumping a little bit ahead. Okay, how about this one? We have to complete squares. So that's the thing we have to do. Negative 2 integral of, here completing square is x plus 1 squared plus 4 then squared dx. Okay. And okay, so now that we have that one, we set this piece here u to be x plus 1, and my integral will turn to 1 over u squared plus 4 to the power 2 du. Okay, now I have 1 over u squared plus 4. Then this is time to use trig substitution. U equals to 2 tan theta, and that will give me an integral negative 2 integral of 2 secant squared theta d theta, that's du. Down there we have 2 squared, which is 4 tan squared plus 4 then square it, and yeah, that's the substitution we did. And now I can multiply everything and simplify. So there will be negative 4 in the numerator, there will be 16 in the denominator, so it will be minus 1 over 4 integral secant square, and one of the tan square plus 1 will go away, so what we will get here is going to be secant squared theta in the denominator, and that is nothing but negative 1 over 4 integral of cosine squared theta d theta. So we are back to one of the integrals that we have. Well, we have done this integral several times, so now the only thing you need to do here is the only thing you need to do here is just apply the tricks that we had there. So that will give me negative 1 over 8 theta minus 1 over 16 theta sine 2 theta. Oh, not theta, just so there are some steps there that you have to be able to complete at this stage. And now we have to go back to the x variable. So this is 2 sine theta cosine theta, but remember that u is 2 tan theta, so that means that u over 2 is tan theta. So the reference angle you have there, this will be u opposite to adjacent, so this will be 4 plus u squared. And what you will find here is negative 1 over 8 is tan inverse of u over 2 minus 1 over 16. This will give me 2, and then a sine is going to be u over that, and then there will be another cosine. This will be 2u over u squared plus 4. There are simplifications there needs to be done, and I'm hoping that I haven't done anything stupid somewhere there. So u now is x plus 1, so I can plug it in back. X plus 1, 2. And this will give me negative 1 over 4. U is x plus 1 over u squared plus 4 was whatever we had at the beginning. If you open that up, you will get x squared plus 2x plus 5 down there, and plus c. So you have that piece, you will have that piece, and we can now add these ones, and that will give us the integral that we had. Okay. So you have to be able to apply all these things and get the integration of the partial fraction.